Okay, so welcome everyone. Our aim today is to somehow go further in our seminar on infinity categories, and I have some good news for you. You don't need to remember anything from what was covered so far on model categories. What you need to remember is the idea of a model category, and that I'm going to recall again. So, is it okay?
Yeah, that's just fine.
Okay. So let me start first by emphasizing why model categories are important. I think in our stories they have two roles. One, because it's a classical way to manage localizations of categories. And second, because they give us a way to compare models of infinity categories. Because the way I see it, infinity categories are like living in a Platonic world, you know, and you can realize them in different ways in mathematics in ZFC. And these ways, of course, you would like them to be independent. Like the notion of an infinity category should be independent of your realization. And you want to compare them. And the way you compare them is using the machinery of model categories. So that's the second role in which model categories will appear in our discussion of infinity categories. Okay, and as an analogy, because I like it, logic at some point, for me, like the idea of an infinity category is like the idea of what is computable. And then you have many different ways to realize what it means to be computable, one by Turing machines, one by lambda calculus, and so on. And then you show that all these models of computation are actually equivalent. Okay, so model categories provide you with the tools to make a similar statement. Okay, so as I said, model categories and infinity categories actually appear as a way to study localizations in mathematics. So maybe a very good starting point is why do we care about localization in mathematics? Okay, so I will recall two main examples, and here I will do everything in the one categorical fashion. So nothing infinity categorical. Okay. Okay. So. So we have two main examples. So one is in homological algebra. And one is in algebraic topology. Okay, so what do we do in homological algebra? Of course, we start with complexes. So these are things like this. So chains, and we have maps. For example, this could be like modules or some commutative ring, and you want that d squared equals 0, meaning the composition of any two consecutive maps are 0. So you can define homology, or in this case probably cohomology is better. And you just define this as the kernel of D. For example, of this D, quotient by the image of the one before. And in homological algebra, the only thing you care about is this stuff. Okay? So given a map between complexes, you get an induced map between the cohomologies. And of course, I will drop writing the D's because they are implicit. And sometimes these induced maps are isomorphisms. So in this case, so if the induced map of F is isomorphism, then we call F quasi-isomorphism. As I said, in homological algebra, we only care about H1, the cohomology groups and the induced map. So if we have a map between complexes, which induces an isomorphism on the cohomology, we would like to view this map as if it were invertible. Of course, in general, it is not invertible, but we would like it to be invertible, so we would like to invert those quasi-isomorphisms. So the people doing homological algebra maybe I will just write HA, homological algebra, would like to study complexes, so maybe I will write this as the category of complexes, and you invert quasi-iso, okay? And that's in some sense the category that they would like to work within. So that's one example where the notion of a localization appears naturally. The second main example is in algebraic topology. So here we have topological spaces, and to these we associate many algebraic invariants. In our setting, the most important one are the homotopy groups and the set of all connected components. And the same story happens if you have a continuous map of topological spaces, you get an induced map from the homotopy groups. Oops. And sometimes these are isomorphisms. And in this case, you would like again to think of this map as if it were invertible, because the only thing that the homotopy can actually sense or detect is the homotopy type of your topological space. So we would like to study in algebraic topology the category of topological spaces where we, so first of all, okay, so F is called weak homotopy equivalence. If the induced map R is bijective for every R. And then when I say this, I also mean implicitly that it induces a bijection on the connected components, because the zero homotopy set is not a group. But I will not every now and then say, okay, differentiate between those cases. You understand what I mean. Okay, so in this case, we would like to study the category of topological spaces where we invert weak homotopy equivalences. So, as you see in both cases, you have a category, you have a collection of morphisms where you would like to invert. The first question is, in mathematics you should ask, is whether this always exists or not. And if it exists, can you describe it in a nice way? So, this takes us to the general setup. So we would like to do localization in general. So the setup is as follows. We start with a category C. And we start with a collection of morphisms. And we would like to construct the localization C where we adjoint inverses to every element of W. Okay? So, what do we mean by this? So, formally, we should have a functor from C to the localization. Let's call it phi W. And this should, of course, in some sense, have the same object. Should be. And also, if you have a, by definition of what it means, a functor, if you have a morphism here, you get a morphism in the localization. So, nothing. But my point is, it shouldn't change somehow the object, ideally. Okay, so anyway, formally, we just have a functor like this, and we would like to have, okay, if you have a functor like this, first of all, you get a canonical functor from the category of functors from the localization to any functor D, to any category D. So maybe I should say we have a functor like this, such that for every category D, we have map like this, and here I put it small w to indicate that these are functors from C to D, which invert every element of W. Okay? So, functor from C to D are not just a set, they are themselves a functor. They are themselves a category, right? So here you have a category, here you have a category, and this is a functor, and you would like this to be an equivalence of categories. So that's what we mean by a localization. Okay, so we want this to be an equivalence. Okay? Okay, so the first thing to notice is, as I said, whether this exists or not. So it actually always exists, up to set theoretic subtleties. Okay, at least if C is locally small. So recall that locally small mean, this means that for every two objects, X and Y, in a category D, so a D is in general any category, and you have two objects, it is called locally small, or if all the home objects are actually sets. Because a priori you can say, okay, they are just classes, but here to say it is locally small, you would like it to be sets. Okay? So what is the proof sketch? Well, maybe to quote Quillen, nothing crazy. But what do I mean? Actually, if you have just a category, you can view it as a graph, and you will have edges indexed by elements of W, and you can just formally add inferences of each element of W. And of course, once you do this, you also need to add further inferences for the compositions and so on. But you can do this, and then you will have some gigantic category or some gigantic graphs that you can interpret as a category, and that's the localization. Okay? So if you want to see some details of this, I will refer you to the homological algebra book by Manin. And someone else, he's famous, but I don't
Gelfand, I think.
Yes, Gelfand, yeah. Yes, so in this book, he had a chapter on derived categories, and he actually starts with discussing localization of categories. Okay, so we have it exists. Thank you, let's go home, everything is done. It is not, because this is usually problematic. This construction, remember, is a little bit problematic. And to see this, we need to think about what are the home classes in this category. Okay? Okay. Remark, if X and Y are, maybe I should say, or actually it is obvious from somehow the construction that the objects of the localization are the same as the objects of C, right? Yeah. So if we have two objects in C, then the objects in the localization are just strings of this form. So you start by X, you go to X1, you go to X2, but in the opposite direction, and you alternate like this. So such stuff.
Zigzag.
Zigzags, okay, yeah. Zigzags. Thank you. Okay, what is the problem? The problem is, in general, our categories, yeah.
Just now, after some equivalences.
Sure, yeah, always. Yeah, thank you. So, the issue is, if your category is not small, meaning if the collection of all objects are not small, this is by no means obvious that it is a set. So it can be a proper class. So this can be a proper class. Okay? And this means it is not a locally small category. It can be that it is not okay, so it might happen that it is not a locally small category. Who cares? You would care if you would like to have something like Uneda lemma. So for Uneda lemma, to work or to use it, to hold, you need your category. Your categories to be locally small. So, although this thing exists, because it in general not a locally small category, you will lose a lot of your mathematical machinery, such as Uneda lemma.
But I think you could probably fix that using Grothendieck universes.
You can do it.
I think the real issue is if you have a category, then the localization might be way bigger, and you don't have any control whatsoever on its size.
Yes, but by saying it is too large, it is precisely saying that it is not.
It may not be locally. No, but the thing here is even if you because if you want to fix this issue with the Uneda lemma with universes, you just take a universe and you embed it inside of another universe, so you have control over that, right? But in this situation, I think like with the localization, it can be way bigger. So actually, you don't have any control over the universes. So you can't even apply it. You can't apply Uneda lemma in that way.
Yeah. So it is. I mean, if you use universes, I think just the same argument will say that it will not live in the next universe.
Exactly.
So that's yeah.
There's also another subtle thing. For example, if you're looking at, for example, commutative rings in a smaller universe and you embed it into a larger universe, you could potentially have more, say, commutative rings that are more complex, and you don't have control over that in any reasonable means.
Yeah. So either case, if you don't like universes, you will have a problem with sizes, and if you use universes, there is also a problem
No
with
control.
sizes. I mean, the issue is universes are just a way to formulate sizes, but if things explode, it explodes everywhere.
Yeah.
I think it is one of those, there is no way to avoid the difficulty.
Yeah.
You have to handle it some way. Okay, so any questions so far? And maybe a small remark. I have said C adjoint -1. I'm sure Cohen wouldn't be happy because last time he would denote this with the homotopy stuff, because for him this will denote the infinity categorical analog. But as I said, I really want to start from the one categorical order. Okay, so we will have problems with Uneda lemma. We will have problems if we want to define anything. How are you going to control this? It is really unmanageable. So model categories come to your risk. So that's what model category do to us. They rescue this situation. So what is the idea of a model category? It is that they provide a setup where we can describe is described in a measurable way. For example, we will not have all these size issues. Okay. So what what is a model category? I'm not going to spell out all the definitions, but I will just give you the flavor and the highlights that you just need to remember for this topic. So what they are, so model category, it is a data. It consists of a category C, 3 classes of morphisms, these are 3 classes of morphisms in C. So these have names. These ones are called weak equivalences. And these are the ones that we would like to invert eventually. These ones are called cofibrations. And these ones are called fibrations. And this data should satisfy some list of axioms that we have seen last time. But good news, it doesn't matter if you recall it or not. It really doesn't matter. What you need to remember is, given this data, you can describe this localization in an easy way. Something that you would like to recall is the following. Being a model category means, in particular, that C has limits and colimits. And as you remember from last time, there are variations. In some boxes, they only require small limits and small colimits. But in any case, you have initial and final objects. So this always you have. Okay? And I will just remind you how these cofibrations and fibrations are related to each other. Because I will mention this later on. So maybe I should... I numbered this one and I forgot to number the rest.
You might want to use brighter chalk, I think.
Yeah, okay. This is just for numbering.
Yeah.
Is it also okay to erase this or no?
Yeah, go ahead.
Okay, so this will be 5. This should be 6. Okay. So the fibrations and cofibrations should satisfy some relation with each other, and these are as follows. Yeah, okay. So if we have a solid diagram of this form, A, B, X, Y, and we have F is a cofibration, and here G is a fibration. So remember, fibrations like to always be on the right, and cofibrations always would like to be on the left. Okay? So if you have such a setup, and moreover, either F or G is in W, then we have a left from B to X. So we have a left like this, making the diagram commute. And why do we impose this condition? It is essentially because, for example, if in the first case, if it's in W, we would like to invert it. So if it was invertible, then you can go in this way and then in this way, right? So that's somehow the motivation. Okay, so that's everything you need to know about model categories. And as I said, they are nice because we can use them to describe the localization. So here is a theorem that formalizes. Okay, so suppose that C, W, co-fib, and fib is a model category. Okay, then we can describe the localization as follows. It is a category whose objects are so-called bifibrant objects in C. And let me recall what is a bifibrant. So given any object C, X in C, as I said, C is a model category, so it has an initial object, which I will denote by phi, and it has a final object, which I will denote by a point. And if this canonical map is cofibration, then we say that X is cofibrant. And if this map is a fibration, then we call X as a fibrant object. And bifibrant just means it is both. Okay? Nice. So these are the objects. So somehow out of all of C, we just disregard all the non-bifibrant objects. Okay? We just take the bifibrant ones as the objects in the localization. And let's describe the morphisms. If X and Y are bifibrant, then the homomorphism set in the localization, how do you define this? So first of all, this turns out to be as follows. First of all, you take the home sets in the category C itself, and then you quotient by some equivalence relation, and let me just write that it depends on X and Y. And this equivalence relation is a homotopy kind of equivalence relation. So to define the equivalence relation, you need to define what is a homotopy, and of course this requires all the axioms of model category. So I will digress on the definition, but the whole point is that the maps or the morphisms are just obtained from the original morphisms by quotient them. So in particular, if this is a set, then this is a set. If this thing is a set, you have a set, you identify stuff, you obtain a set. So it actually becomes smaller, not larger. And that's somehow the novelty of what is a model category. At this moment, if we were only concerned about model categories, we will discuss the main two examples, the topological case examples and the homological algebra example. It leads to like derived categories, and many theorems that you know from homological algebra is just a special case of this. So, for example, what is a bifibrant object in topological spaces? CW complexes. So you will have a lot of theorems from classical homotopy theory as a special cases of this machinery of model categories, as well as classical theorems of derived categories as a special case of this. But since we are not mainly focusing on model categories, I digress as well. Okay. Yeah. So I had a few remarks here, which I said some of them. So in general, if we start now with a locally small category, the localization is guaranteed to be a locally small category, right? And I think there is a point here which deserves some clarification, which is, in the beginning I made some construction, and supposedly both kind of constructions, the one using like managable and here, they are somehow the same. And remember, this being the same, it means equivalence of categories. So you can disregard as many objects as you wish, as long as they are in the essential image. So there is no contradiction. But this just tells you a way to actually make this disregard in a factorial way and everything works nice. Okay. So, since this is a homotopy kind of relation, equivalence relation, people usually say, oops, so maybe, I don't know, notation, convention, definition maybe. People also sometimes refer to this as the homotopy category of C. And the reasons we call it like this is just because of this. It is obtained by this equivalence relation, which is a homotopy equivalence relation. Okay. Now a very important remark. So given a model category, you obtain its localization. But to do the inverse, or to go the other direction, it is not unique. So you can have the same localization obtained from various model categories. That's why it is called a model category, because it models the localization. But it is not unique. Like you can have different model categories with the same localization. And this will be, I will give an example later on when we discuss topological spaces and simplicial sets, and this will be like the kick-off towards quasi-categories.
Can I ask?
Yeah, please.
So usually in this construction you want a map from C to CW inverse, right? Like
yeah.
So if I'm choosing just cofactorate objects as elements here, so for each object, there is
there's something called the vibrant
cofactorate object. Yeah, there's a weak equivalence there.
Yeah.
But this object is not unique in this topological sense. Like there could be like a lot of them. Then you have to make a choice for each object, because I need to. So my question is more set theoretical. Like if you are working with like a really big category where the objects are not actually sets, that means you want some kind of axiom of choice for classes. Is that true? Like
so the way I think this is actually, I guess, a technical point, and I think the way it is done, for example, in one book, is that they have what is called factorization systems as part of a data of what a model category, and so this becomes part of the data that you provide for the model category. If you just assume it exists, it should be treated in another way, but I haven't read the details. But if you provide these factorization systems as part of the data, somehow this cofibrant replacement becomes canonical.
That does exist.
That does exist, but to make it factorial in a cheap way, you provide it as part of the data.
No, but with regards to the axiom of choice, so there is like a global axiom of choice for classes, but then there's also like an axiom of, like various versions of the axiom of choice for universes as well. So I mean, if you want to, I mean, depending on which like foundation system you're using, you have.
I don't think about these things, but just like I wanted to.
Yeah. But also in general, in category theory, when we define an object, we really define it up to canonical isomorphism. So all of these cofibrant replacement will be canonically isomorphic.
Okay. Not entirely, I don't think so.
But they are isomorphic at least.
They are isomorphic, and I think if you pass the homotopy category, then it's canonical.
Okay.
And like sometimes you require as part of the datum in a model categories that you have factorization systems that are functorial. And then they are functorial in the model categories.
Yeah.
But I think I've read somewhere that there are model categories where there are factorizations, but they cannot be chosen in a factorial way, so maybe.
Well, in Quillen's like original work on homotopical algebra, he gives like a few examples at least, because he doesn't include functorial factorizations as part of the axiom. But then, like, we don't, like, I mean, if you only care about algebraic topology and like chain homological algebra, then I think it's fine. You don't have to worry about
So just to give an example, in homological algebra, this would be like given a module, you have like a projective resolution of it. And even though the projective resolution is not unique, it's of course not unique, but it is unique to up to isomorphism. So in that sense, you can define this functor. And I think the whole point is you shouldn't think in the one category of categories. You should think about it in the two category of categories, because when you say a functor, you should view this inside the category of functors. So it is determined up to a natural transformation. So if you have that point of view, it becomes natural that you don't have a one fixed cofibrant replacement. Okay, now, since ultimately we care about homotopy categories of model categories or the localization, a very natural question is, given two model categories, how do we ensure that their homotopy categories are the same? Okay? And this requires the notion of a Quillen equivalence. So a Quillen equivalence between model category will be some kind of an adjunction such that it induces an equivalence between the homotopy categories. So this wasn't covered before, so let me just tell you the definitions. So should I write the question, or is it okay what we are?
I think it's okay. I mean, it's recorded, right?
Okay. So I think we're done with this. Yes. So let's discuss very quickly Quillen equivalences. Okay. So the setup is that C and C prime are two model categories. Okay. First, we define a Quillen adjunction. Between C and C prime, as well an adjunction, a pair of adjunction functors. So let's write this like this. So for me, this means that F is a left adjoint to G, and G is a right adjoint to F. Okay? And such that one of the following equivalent conditions hold. Of course, maybe I should say this is a proposition definition at the same time, because I make an assertion which might not be obvious on the first encounter. So the first condition is that F reserves cofibrations and trivial cofibrations. Maybe I didn't remind you of what is a trivial cofibration. So this just means it is the intersection of cofibrations and the weak equivalences. So something which is both a cofibration and a weak equivalence is called a trivial cofibration. Some people call it a cyclic cofibration. Okay, so that's the first condition. So F reserve cofibrations and the trivial cofibrations. The second condition is that G preserves fibrations and trivial fibrations. And again, trivial fibration means it is a fibration and a weak equivalence. And the third thing is that it induces, so F and G induces an adjunction from from the homotopy category of C to the homotopy category of C prime, and these are called the derived functor. So this will be called the derived functor of F, this will be called the right derived functor of G, and of course again, if you look again into the case of homological algebra, this actually is a derived functor that you know from homological algebra. So again, it is marvelous that you can encode all of this homological algebra in just categorical fashion. I really like it. Okay, so this is what we mean by a Quillen adjunction. So the take-home message is a Quillen adjunction is just an adjunction on the model categories which induce an adjunction on the homotopy category. Okay? Nice. So this is 6, 7, 8. So how are we time-wise?
Like 45 minutes left.
Hmm?
Yeah, 45 minutes.
Yeah. So I just spent half an hour. Right?
You spent 45 minutes because.
We started, okay, we started on the clock.
Yeah.
Actually 5 minutes later, no worries.
Yeah.
Okay, so that's what a Quillen adjunction is. And, okay, so what is a Quillen equivalence? So I will have the same setup, so I will have two model categories, and a Quillen equivalence maybe from C again to C prime is a Quillen adjunction such that given A in C and B in C prime, so amorphism from FA to B in C prime is a weak equivalence. If and only if. So remember that we have an adjunction. So this data is correspond to a map from A to GB, and we require that this is also a weak equivalence. So somehow that the adjunction moves back and forth between weak equivalences. Okay, why this is important? Because of the following theorem, and which is the most natural thing you should expect. So essentially, this will say that if you have a Quillen junction, this derived functors induced on the homotopy categories are equivalents if and only if the original Quillen adjunction was actually a Quillen equivalence. Okay? So let's phrase this. So the following are equivalent. Again, the same setup. So F and G are Quillen equivalences. Second, LF and RG are equivalences. And when I say they are equivalences, I mean in the standard notion of category theory. Okay? So, just a fun remark. Remember, Quillen adjunctions are adjunctions, but Quillen equivalences are not necessarily equivalences. They are equivalences on the homotopy category. But here I didn't say that this is an actual equivalence between the model categories. you get an equivalence once you go to the derived world, but on the non-derived world, they aren't equivalences. Okay, and again, this to justify the notion of or the terminology model category, because here you see that what you care is the homotopy category, and you can have several model categories which are Quillen equivalences, but as categories they are different, right? Okay.
Can I ask you a question?
Yeah, please.
So the left and right adjoint, the functor, left and right derived functors always exists for functors between.
Yes.
Yeah, by universal property.
Yes.
No. I mean, in this sense, like the way you would.
I mean, it is here. It is just a definition.
Okay.
I say you have a Quillen adjunction if you have an adjunction which induces an equivalence. Which induces an adjunction on the homotopy category, and then I call this induced adjunction as left and right. As a left
derived functor.
Derived functor and right derived functor.
Yeah.
But there is also a different way to define derived functors in general, right? Like,
Yeah.
this is. Yeah, we will discuss this.
Yeah, this is related to this replacement functor. This is probably what you mean.
Yes.
Yes.
I'm a bit skeptical about your claim that it's just universal properties, but you don't really ask that they preserve all the weak equivalences, only like weak equivalences that are cofibrations or something. So I guess maybe you have to say that by saying that they induce a junction, you're saying that you let them induce in a certain way, and that being well defined, maybe that has to be part of the condition.
So I'm not sure. Here there is really nothing to show. It's just a terminology. So there are two notions of derived functors here. One in a specific model category.
Yes.
That's probably what you have in mind.
Yes.
And that's what appear in.
But you're saying this is not that derived functor which I usually.
Here you have two derived model categories. So that's here different from what you have in logical. That's comparing model categories.
Yeah.
So maybe I will say one or two words. So ideally is you have C prime, okay, and you have something like this. And you have the localization. It would be a beautiful world. It would be a beautiful world if we can fill this.
Yeah.
Yes.
Yes.
But we can't.
Yes.
We can't.
Yeah.
Okay? So somehow these functors are the best you can do.
Yeah. So my question is, so the definition you are giving here means this is the usual way of thinking the derived functors in any kind of category. There is this derived functor in terms of I have a functor between these homotopy categories such that it satisfies certain universal properties and there are my question is that in generally this derived functor does not always exist for any functor. For example, like you need to have left exact functors for the left derived functors in the usual.
Yeah, but here existence is precisely included in this nice property. So if you have functors which satisfy this, then yes.
Okay.
So you can say existence is equivalent to these conditions.
Okay.
And that's why I think that's actually a definition / proposition, because there is something non-trivial here.
Okay. Understood.
Okay? Is it okay now? Yes. Okay. Now we do examples. Am I going too slow or too fast, or is it okay?
It's okay.
Okay. So recall that here we have the category of topological spaces, and we have weak equivalences are just weak homotopy equivalences. This example was discussed last time, I guess. And I have already recalled the definition of what is a weak homotopy equivalence in the beginning. And here the vibrations are so-called Serre vibrations. Okay, so what is this? So you have dn, this is like the standard n-dimensional disk, and you have its canonical map into the cylinder above it, and here you have a map f. So f from x to y is Serre vibration. If given such a diagram, you can lift this. So in some sense, it satisfies, not actually, in some sense, it satisfies the right lifting property of these inclusions. So these are the vibrations, and as you remember, given a model category, you can determine the co-vibrations by knowing the vibrations and weak equivalences. So here I have given you the weak equivalences, I have given you the vibrations. You can, using the axioms for model category, know what are the co-vibrations, at least morally speaking. And as you also remember, proving this is non-trivial. So defining a model category is easy, providing non-trivial examples is not easy. Yeah.
What are the inclusions from dn to x or dn?
So yes, so here you have a map x into x0, for example. It is really, if you have like something like this, you include it in this way.
Okay, but from dn to x.
So dn is just an n-dimensional disk. So here I just give one-dimensional disk.
No, but he's asking like what are the maps from dn to x and dn and the cylinder to
This
y.
is for every map, like for every
all maps
solid
such that the
diagram.
diagram commutes.
For every map F and for every map alpha and beta, such that the solid diagram is commutative, you can have a lift.
Okay.
And with respect to this model category, it's very easy to notice that all topological spaces are fibrant, right? Because being fibrant means that you would like this object to be a vibration, and you would like to prove something like this, and you would like to have a lift like this. But remember, here you have a projection map, which just projects the cylinder into the base, and then you can take this lift as just this composition, and then it is actually the lift. Okay, so every topological space is fibrant in this model structure. Okay, and the rest of my talk will be a trial to justify or explain the following result. Okay, so theorem. So there exists a Quillen equivalence between topological spaces with this model structure and simplicial set. And here is this functor is called the simpler chain complex that you know from algebraic topology. And here this is called the geometric realization. Of course, I haven't told you yet what is a simplicial set. And to explain this result, we will now start talking about simplicial sets. Because of course, to define quasi-categories, they are also a simplicial set satisfying some properties. So, and I think that's something to keep in mind, because it will be relevant. And why it's going to be relevant? Because in general, again, recall that the notion of an infinity category, or actually infinity line categories, is a Platonic notion, and you can model it in different ways, right? And there are at least 3 ways to do this. Actually, I need a full blackboard, so let me write a diagram. So before I do the diagram, first of all, my aim is to tell you about simplicial sets and tell you what is the model structure here. And in the meanwhile, we will develop more stuff about simplicial sets that we will use it.
Probably yes.
Okay? So this was 8, here is 9. Okay, so the diagram I would like to have in mind is here in the Platonic world of Platonic forms, you have a notion of infinity one categories, and you can project this into, maybe I will write it here. So everything outside of this bubble is just maybe ZFC. Okay, so mathematics as we know. Okay, and here you have topological categories. Here you have so-called simplicial categories.
What do you mean by topological?
I will explain everything. I haven't explained something. I just put this here for reflection. Okay? And here you have, maybe I have made it too big. Maybe the Platonic world is not that big. Here you have quasi-categories. So the whole idea is this notion of infinity one category can be realized in 3 different ways, at least. Topological categories, simplicial categories, and quasi-categories. Our main aim was to reach here. Okay? First of all, as I said, you would like these to be equivalent in some sense. So what we will do, or actually what was done, that you can construct functors between these. And this one is actually a composition of those, so maybe I will just write it in different color. And the whole point is, you can define model structure on simplicial sets, and you can define a model structure on simplicial categories and on topological categories, such that these functors are
Quillen
equivalences. Okay? And the infinity categories will be the bifiber total. So what are these functors? Let me just write the names. First of all, this I will write it like this. So you might remember this, but here, okay, so maybe what is a topological category? Topological category is just a category, but instead of having home sets, you have topological spaces. So it is a category enriched over the category of topological spaces. Simplicial categories means it is a category enriched over simplicial sets. Okay? And quasi-category mean it is a simplicial set satisfying some properties that we will define later on. And if you just forget now the quasi-categories and you have these two, in this world, home sets are topological spaces. Here, home sets are simplicial sets. So you can apply this to the home sets to move from one world to the other. And this will provide you with these Quillen equivalences. And here you can define also some functors. Let me just write the name. So it is one of them is written like this, like some kind of scripted C.
Okay.
And I think this C comes from a name of some guy, but I don't recall his name now. Do you know his name? He was the one.
Not Szynski, I don't think.
No, one older than him.
Retzschner or something.
I don't remember.
Charles Resch, or maybe.
No, not Charles. Someone older, but anyway, it is C for some dude. And here you have.
I think you have a lot of arrows on in the other way around.
Which way?
Singular, for example, should go from topological to simplicial.
Yes. Yeah. Well, here I have them correct. My notes. Yes. So let me check. Also this is done wrongly. Yeah. I think I flipped all the arrows. So here you will have so-called coherent homotopy nerve. Okay. So this is somehow the holy grail of infinity category. There are other models of infinity categories, so you can define them as A infinity categories or whatever. Our path will start from the general idea of what is a higher category theory, and then we will say, okay, whatever infinity one category should be, for sure, and I will explain why it should be a category enriched over infinity groupoids, okay? And then using Grothendieck homotopy hypothesis, we know that these correspond to homotopy types. But if you just enrich them over homotopy types as a one category, you get the wrong thing. So the idea is to try to model these homotopy types by topological spaces, so you get the notion of a topological category. This will come up later on in more detail. So we will start by saying, okay, maybe as objects, infinity categories are just topological categories, but the problem is, yes, they give you what is an infinity category, but functors are wrong. Like if you just use the notion of what is a functor from enriched category theory, you don't get the notion of functors that you would like in this Platonic world. Okay? So our aim is to move forward and forward to quasi-categories. So the first step is we will go to simplicial categories. And from there, we invoke this homotopy, coherent homotopy nerve to go to quasi-categories. And you might think, okay, this is just for psychological ease. Yeah, we know how to motivate this idea of a quasi-category. But actually, especially this direction is quite useful. Because how are you going to construct quasi-categories? For example, of course, you can do some examples. So any one category is an example of one category. Every topological space gives rise to one. But to construct, for example, the infinity category of infinity categories, or the infinity category of anima, or infinity category of spaces, the easiest way that I know in this world is to invoke this homotopy coherent nerve and start from some simplicial category, actually can enrich category and invoke this. So this is important for psychological, philosophical reasons, but also for practical reasons. Okay? So, back. So this is what we are aiming to, and this is, as you see, is part of this one. And so now to do anything, we just need to start with simplicial sets because it appears all over the way. So now my next step is to actually start telling you a little bit about what is a simplicial set. Any comments, questions?
Yeah, I guess maybe we should give a comment. Maybe I should say something about what happens after we get to the definition of a quasi-category. So once you cover the definition, and I think maybe say something more than just the definition and prove like a few things, then we will start with the synthetic approach to infinity categories, and this is something very, very recent. And we'll cover that for a little bit. However, that in itself is very highly motivated by work on complete Siegel spaces, which is another model of infinity categories closely related to quasi-categories.
Yeah, but in my talks, I'm sadly not going to talk about complete Siegel spaces.
That's where
yes, but the good news is to define them also you need simplicial sets.
Exactly, so all of this will eventually be very useful.
Yes. And also to say a word on this synthetic approach, my understanding, very limited understanding is, one way to motivate it is you construct this infinity category of infinity categories using these quasi-categories, and you try to somehow axiomatize it. So you will prove many properties, and then you realize if God gives you the infinity category of infinity categories, you can recover everything else.
Yeah.
You can recover individual infinity categories, and then you can recover a notion of four-scan complex topological basis sets, so you can basically recover everything. So the whole point will be to eventually axiomatize this infinity category of infinity categories and use it as a foundation of mathematics. And I think that's somehow what this synthetic approach is all about.
Exactly, and but the issue with starting with that right away is that a lot of the arguments and many of the axioms are not very well motivated.
Yeah.
Basically, pullbacks form like the backbone of many of the proofs, right?
Yeah,
but in order to see how pullbacks come into the picture, you need some experience with the models themselves.
Yes. However, I would say ZFC itself is not very well motivated. So you start somewhere.
Yeah, exactly.
Yeah. Anyway, that's we are rushing too much of ourselves. So now let's talk about simplicial things. Okay. So first of all, I need to tell you about the category delta, which some people call the category of combinatorial
like the simplex category, I guess.
Simplex category of combinatorial simplexes, whatever. So simplex category. So what is this? This is very easy. So it is a category. So delta is the category of all finite, totally ordered sets plus morphisms are order preserving maps. So, as an example of an object here, you start with a natural number and you define this bracket n to be 0, less than 1, less than 2, less than n. So this means that this delta as this bracket n is just a set from 0 to n, and you define an order, the natural order from natural numbers. Okay? And it is an obvious remark that any finite totally ordered set is isomorphic to an object of this form. Right? So, essentially, when we define, for example, a functor on this delta, it suffices to define them on this object. Okay? So somehow I will confuse between delta, the objects of delta, and this, because somehow this gives you like what is it called? Skeleton of the category?
I mean, every category is equivalent to its skeleton, so this, I mean, that just formalizes this.
Yeah, so this is a skeleton of the category. And of importance role are specific order preserving maps. I think everyone here knows what is an order preserving map. So I'm not going to define it, but I will give you some examples because they will appear. So let's define the eyes coface map. So suppose that we have, first of all, probably my notation is not a standard, I didn't look it up. So if you have n is a natural number, we define a map like this, and it is defined to be the unique injective map such that I is not in the image. So my claim is there is a unique map from bracket n minus 1 to bracket n, which is injective, and where I is not in the image. And that's very easy to see what it is. So concretely, delta I of j, to define it, you have to do it in two cases. First, if j is less than I, then this is just j, and you just add 1 if j is larger than or equal to I. So, how to visualize this? So here we start with n minus 1 bracket, and here we have the n bracket. We have okay, and here as well. So by these dots I just mean 0, 1, 2, and here we have I minus 1, I, and here we have n minus 1, and here similarly we have n minus 1, and here we have n, and this map just tells us that it is the most boring thing ever. Okay, and then you don't map I to I, you just map it to the next one, so I plus 1, and you just start shifting everything, and this shifts. Okay, so this is concretely what it means. So this is called the co-phase map, right? So I forgot to write that this is 10. So this one is 11. This one is 12. Okay. So the second example is the code degeneracy map. By the way, is it okay for the camera?
Yeah, I think this is
No?
too dark, I think.
Too dark?
Yeah.
But that's good, right? Okay, anyhow. So,
I think using white might be the best.
okay. So this is just say code degeneracy map, and this is defined. So I is a number from 0 to n, n minus 1, and then we define sigma I is a map from n to n minus 1, and it's again defined to be the unique surjective map such that if you just take the pre-image of I, it consists of I plus 1. Of course, implicit, when I say map here and here, I mean order preserving map, because I work in the category in the simplex category. Okay, so what does this look like? Again, for concreteness, maybe I should put I here because this is the I's code degeneracy map. So sigma I of j is just, well, j if j is equal than or equal to I. It is j also if j equals I plus 1. So maybe I should here say this. I was drunk yesterday, maybe. I wasn't, but anyhow. So it is defined like this concretely.
It's I up there, not I plus 1.
Where?
So when j is I plus 1, it's supposed to be I.
Yeah.
So it's I plus 1 minus 1. If it's greater than I,
You mean here?
yeah, it maps j to j if j is less than or equal to I.
Yes, and if I is I plus 1, it also maps it to j, right?
Maps it to I, so it's I plus
Yes,
1
okay.
minus 1. So it's this,
Okay.
this is the second case.
Yeah. Well, I mean, you can erase the middle thing, I think.
Just do less than or equal in the first line.
Are you satisfied like this?
Yeah, I think it's, yeah, this is fine.
Okay. So anyhow, again, you are given something like this, and then you start having identities until you go to I and I plus 1. You just map them to the same, right? And then everything to the left. Okay, so that's how it is visualized. Okay, now, why I'm talking about these specific maps? Because of the following fact. So if is a map, a morphism in delta, then you can write F as a composition of delta i's and sigma j's. So somehow you can factor every F as a composition of those, and you can see that these maps satisfy some kind of simplicial relations, which I'm not going to write because they are not important for us. You just know that they exist, but since we are not going to use them as an exercise, I am purposely not going to write them now. Okay? And I think that tells a message. You shouldn't remember them. Anyhow, so now we have all these definitions. Let's define now what is a simplicial and a co-simplicial object. So suppose C is any category. So we make two definitions. So a co-simplicial object in C is a function from delta to C. Just a function. And a simplicial object in C is a functor from delta up, the opposite category of delta, to C. The first time I have seen this, I was confused because it is like, I don't know, I was confused because I would say this should be maybe simplicial, but it is what it is, and I think it is, we should think of simplicial objects, actually they are pre-sheaves on this simplex category. So that's what we are eventually interested in, but these ones will be very important to us because as you will see maybe today, maybe next time, depending on the time, many adjunctions will be proven by just saying, hey, I have a co-simplicial object in this category, and abracadabra, you have an adjunction from simplicial sets to somewhere else, whereas this somewhere else is a co-complete category. So that's also something I really like. It is a lot of abstract nonsense, but just imagine, to provide an adjunction, I give you some co-simplicial object. And it's not just like useless functors, but actually it will give you very natural functors that to define them concretely. It will take you some time, and it will not obvious that these are, at least it will not be as obvious as this one, because it will be somehow by construction true that they are adjunction to each other. So anyway, so now we have defined this categorical notion. We denote CS as the category of simplicial objects So given a category C, I just add S before it to say this is a category of simplicial objects. And what are the, of course, the objects are simplicial objects. And morphisms are just natural transformation. So remember that this is, for example, here is just a functor like this, and a natural transformation. So if we call this alpha, so and we given alpha and beta, a morphism is just a natural transformation between these two functors. Okay? And finally, what is a simplicial set? So what is the category of simplicial sets? It is this one. It is simplicial sets in sets. So this is just the category of simplicial sets. I know I am near the end of my time, and I really don't like to go over. So what I will do now, I will just tell you concretely what is a simplicial set, because maybe some people don't like this categorical language, and then I will stop, and next time we continue with simplicial sets. Okay? Okay. So do you want me to write this more down? What do I mean by a natural transformation or anything? Okay. The problem is I don't, although I number my blackboard, I don't number my notes. So now I'm confused where I am. Okay. So maybe let me tell you first what is an example of this. The most boring and the most useful example. Okay, so examples. So suppose we have n is a natural number, and we have this object, of course. We can just take the representable functor represented by this one. So this we can define delta n as just hom in the simplex category. So what is this? We call this is just a functor from delta up to simplicial set, to sets. And concretely, delta n of m is just the normal thing. So this is of course a set, right? And maybe a piece of notation. If x is a simplicial set, I will just write x sub n to be x evaluated at this bracket n, right? So we can also write this as delta n all sub m, okay? And maybe I will finish with this concretely, maybe before concretely. We call this thing, sorry, we call this the standard n symmetries. Okay? So concretely, a simplicial set is just a bunch of sets indexed by natural numbers, and so we can write them like this, and some maps between those ones, and these maps come from those degeneracies and co-degeneracies, co-faces and co-degeneracies maps. So here you will have two maps. Here you have three maps, and you have two maps in the opposite direction here and one map here, and of course you have further stuff. So what are these maps? So maybe first I define in general, if X is a simplicial set, I write dr to be X of delta of I. Remember I defined this co-phase map, and this was a map in the simplex category, and if I evaluate it under the functor X, I get a map which I denote di, and I call it the I's phase map. And similarly, I get so-called the I's degeneracy map, which is just X of sigma map. Okay? So if I know these maps, which I do because X is a functor, these are D0, D1, and here I have D0, D1, D2, and this one here is just S0, S0, S1. And